In this video, I want to talk about write-ahead logging, which is a concept that's super important for database recovery in database management systems. But first, I want to clarify a couple of terms and also define a new one. So this term of write-ahead logging actually refers to a computer science concept itself, which sort of refers to this process of, flushing things to permanent storage and using it to recover a database. However, the actual acronym of WAL itself is something that in Postgres actually refers to the write-ahead log. And that actually is a specific log that has a very specific purpose. But the reason I want to point that out is because in Postgres, if you're reading documentation or anything, you might see something called the transaction log. And these are actually interchangeable. They are the same thing. The write-ahead log and the transaction log are the same thing. So even in this video, I might refer to the transaction log. So you should just know that that actually is the same as this WAL. So to clarify, again, that write-ahead logging is its own separate concept, but it is relevant for the write-ahead log. The other actual term that I want to define is the xlog. So the xlog we can think of as just sort of a log that records some sort of information about the database state as well as transaction information. So if you're unfamiliar with some of the words I just used, like database and transaction, I recommend watching the multi-version concurrency control video that was published earlier on this channel. That kind of starts a lot more from first principles. But generally, you should be familiar with what a transaction is and what a database is. And this is sort of just a statement. This xlog is just sort of a statement that contains some information about those things. So to understand the importance of write-ahead logging, let's walk through a scenario where a crash happens in a database, and you'll start to understand why introducing this procedure is actually super important. So below, I have a diagram, and just to sort of shout out where I got this diagram from, I've been using Suzuki's Database Internals textbook from Postgres as a tool for sort of learning about a lot of these things, and all of the pictures in this video are from that textbook. But to walk through this example, we have a database cluster here, and we have a shared buffer pool. The database cluster we can think of as just sort of the disk, the actual place in memory where our information is being stored, a physical place where we have all of our information. The shared buffer pool we can think of as just sort of a cache almost, just sort of a temporary access of whatever is in disk. So first, we pull our table from permanent storage, from the database cluster. We get table A here. And then we begin a transaction. And then we insert the value A into this table A. And then we commit the transaction, and we do the same thing again, but with the value B. We start a transaction, insert that value, and then commit. And then, it looks like our database crashes in step 3. So this is really bad because all of this information that we've just inserted into table A could be lost because of this crash. This becomes really problematic, especially when you have really, really big database systems with very important information that might be more than just, A and B in a table. And so when we have crashes, we have to have some sort of system implemented that makes it possible to recover the database and return it to its previous state. So that's where write-ahead logging comes in. So what I'm going to do is separate these two and actually introduce a new layer, which will be thought of as the write-ahead logging sort of part of this procedure. So now that I'm splitting these two, what I'm going to do is I'm going to add 2 new layers. The first will be the WAL buffer, and the second will be the WAL segment files. And these we can think of as just sort of their own little layers in this process. And now let's walk through the exact same scenario again, but with these 2 new layers introduced. So first, we want to pull our table from the database cluster. This happens the same. We still go to the disk and access it and then pull it into our sort of shared buffer pool cache. And we're looking at table A now. And now we begin our transaction like normal. We insert into table A value A. So this happens. But as this is happening, what we do is we actually write an xlog, remember that term from earlier, to this WAL buffer. And in the same way that the shared buffer pool that we've been looking at is sort of a cache, like a temporary look at what's going on, the same exists of the WAL buffer. This buffer is just sort of a cache of recent storage, of recent logs that will be flushed to permanent storage later. So we add an X log here to the WAL buffer that basically just tells us, hey, we inserted this value A into the table, and then we commit. But as we're committing this operation, as we're committing this transaction, what happens is we flush this WAL buffer into the WAL segment files, essentially pushing it to permanent storage. So now we've committed this operation and we've officially moved it to a place where it'll stay permanent. Then the same thing happens with our second transaction. We begin, we insert the value B into this table, and as we do that, we add an X log to our WAL buffer, and then as we're committing this, we flush it to permanent storage, to the WAL segment files. So you can kind of see a general pattern here about what's going on, but essentially what this commit tells us is that we've already moved things to permanent storage. We flushed things to the WAL segment files. And that's what that word sort of commit can tell us. Not only does it tell us that our changes have actually been sort of pushed to the database and that they're reflected there, but they also tell us that the write-ahead logging system has actually taken note of what we've done. So now the crash occurs. So step 3, the sort of big incident that we've been awaiting, the crash happens, and now we're sort of wondering, how do we recover our data? But the good thing is, now that we've introduced these two levels of the write-ahead logging system, we have a method for how we can actually recover our data. Because it hasn't been completely removed and destroyed, our data still exists. It's actually still present in these two areas of permanent storage in the disk. We're going to talk a little bit more about what that looks like specifically in a minute. But to give you a little more context and a little more specificity of what these two layers actually are, specifically the WAL segment files, I want to point out that if you care about the specifics, these WAL segment files are a series of 16 megabyte files, typically broken up into 8 kilobyte pages. And obviously it's a lot more than 2 or 3, but I can't write out every single one of them, but you kind of get the idea. There's these sort of 8 kilobyte pages, and those sort of make up this larger 16 megabyte segment file. And those all contain sort of X logs of information that contains database state information, transaction information, things that we need to actually recover the database. But now I want to talk about a sort of separate procedure, just sort of a process that's happening at this time that's really important for understanding the general sort of database recovery aspect of this whole thing. So specifically, I want to talk about checkpoints and the check pointer. So the check pointer we can kind of think of as a sort of a background process. And actually this specific part, just checkpoint, is a command that you can issue as a Postgres user. So the checkpoint, in the same way you could imagine there's some transaction that's surrounding this. There's some begin and some commit, but this checkpoint command essentially writes a checkpoint record to the current WAL segment. So if you remember our two layers, we have that WAL buffer, and then we have the WAL segment files. What this checkpoint command tells us is, hey, let's mark this point as a checkpoint. So we would go to the segment files and say, hey, there is a checkpoint here that we need to mark. So specifically, one thing that's really important to note here, and a really important aspect of this sort of checkpoint process, is the redo point. So the redo point is the location where we write the xlog record at the exact moment when we sort of initiate this sort of checkpoint command. So it's essentially the answer to the question of where do I start the redo when we're trying to recover from a crash. So you can imagine a user issues this command, this checkpoint command. Immediately we should know, hey, let's log right here as the sort of block point of saying, hey, everything from onwards from here is what we're storing as sort of the changes since the checkpoint. This redo point is saying, okay, let's say some crash happens. Where do I start? If I'm wondering where to start, I check the redo point. Let's go back here to the beginning. And this is where I need to start over from. So this redo point is really, really important for understanding the order in which a lot of these changes are going to happen. So let's sort of walk through where these changes actually come into play. So I'll clear the screen just a little bit to make it easier to see. But the check pointer, like we were talking about, is actually like in its process of changing things, flushing things to permanent storage, actually updates another file called the PG control file. Now this file is super important, and to note that, I'm just going to put a couple of asterisks here. And specifically, the reason this file is important is because it kind of dictates how our database recovery actually happens. And it does that because it contains two really important pieces of information. The first is sort of this checkpoint xlog, which is exactly that sort of where is our checkpoint, where do we start over, where do we redo our changes from. And the second thing is the database state. Now, specifically, database state can be modeled as one of three things, which is one, either startup, which essentially means that the database is starting currently. Then there's shutdown, essentially meaning the database is not functioning anymore. It's stopped. It's not in use currently. And then the last is in production, which we can think of as just sort of a state that says the database is being used currently. So in general, we have some idea as to what this WAL process, this write-ahead logging process, is kind of doing behind the scenes. But to emphasize how robust this process is, there's even something that happens in the background where if an entire page is corrupted, there's something called full page writes, which will write the write-ahead log. We'll write to the write-ahead log the full page block and just sort of overwrite the pages that you're trying to recover. There's some specifics behind the differences between what we just talked about and that full page write, but in general, the idea is still the same with, generally moving things to the WAL segment files into the WAL buffer. So it's not too much to really worry about. The general idea is still the same. But now that we know the way that we're writing things to permanent storage, there's one other process that we need to understand, which is the WAL writer. So the WAL writer is a background process that periodically just sort of checks the WAL buffer and writes all of the unwritten xlog records to the WAL segments. So we move the xlog records to here, I'll clear some of this up. So if you remember, essentially we have that WAL buffer that's on top, and then we have the WAL segments below, and those are the two new layers that we introduced. So you can imagine there's some buffer that's up here, and then we have the segments down here, the files, and let's say this buffer contains like different blocks of information, and inside of these there's xlogs over and over again. Essentially what our WAL writer does is, we can draw our little WAL writer as some smiley face. It's walking through this and checking, hey, are there unwritten xlogs here? Has there been information in these xlogs that hasn't been flushed over here to permanent storage? And if there hasn't been, then we push it. This is the simple sort of background process that exists in Postgres to do this. And this sort of just emphasizes in general how much thought has been put into a lot of these systems. So Postgres specifically has the WAL writer enabled by default. So it works in the background, and it doesn't really interfere with what's going on a lot of the time. And it is a super critical component of making sure that we can recover from database crashes. So now let's think about how we can actually recover a database if we do go through a crash. So if you remember, we have our PG control file here. So PG control is up here, and then we have sort of step 1, step 2, and step 3. We're going to walk through each of these steps. So the first step is booting up our system. So if you remember, we have our database state inside PG control, which can be modeled as one of 3 things, either startup, shutdown, or in production. So the reason that's important is because if we boot up our system and it says it's in production, then we know that something went wrong. If our database system crashes and we boot it up and it does not show that it's shut down, then we know that our system was able to shut off in some incorrect way. And we know that it's in production and we need to actually do some sort of database recovery. So that's when we move on to step 2 and we try to move on to the checkpoint. So the checkpoint will tell us, hey, this is the last sort of marker of database state that we want to record, and everything onwards has been what's happened since. So what we try to do is check if this checkpoint record is invalid. If it is, then what we do is we simply just go back to here, this redo point, and we can replay changes from here. This is sort of some other information that's kept in PG control. It basically just tells us like, hey, if the most recent checkpoint is invalid, we just go to the checkpoint before that. And if this is invalid, actually, we just kind of give up. We don't actually continue along with this process. The only information we store is this like 2 most recent checkpoints. So after that, what we do is probably, or well, I'll summarize that. That's checkpoint valid. We essentially determine whether or not it's valid and determine which checkpoint to return changes from. And the last is we replay the X logs. So if you remember, we had those X logs which have been flushed into permanent storage into the WAL logs. And so essentially all we do is we replay those X logs. So you can imagine there's X logs here. You can see there's X log records right there and right there. And all we do is we just essentially play these X logs. You can imagine that's like changing the database state in some way. According to our earlier example, maybe that means we insert A, and then this X log could be insert B. But essentially you could see like how as chronologically as we move through these things, we return the database to its original state or to its state pre-crash. Now, there's a lot of specifics behind this process. In fact, there's actually some more information on, whether or not we should replay every single one of these X logs here, but it's a little more complicated, and I didn't want to go too into the specifics for this video alone because I think there's already a lot of content in here. But in general, this is the idea behind how we sort of use X logs over and over again to restore the state of the database. Now, one other thing I did want to throw in as an extra tidbit of information was about these WAL segments. So if you remember, again, we were iterating through the WAL segments here. Those are those sort of permanent file storage pieces of information that store these X logs. So actually, the way those WAL segments work is they are reused, and they're also dynamically created according to how we use WAL historically. So what I mean by that is we actually can estimate the expected number of WAL segments that we need based on, previous checkpoint information. And we can expect, hey, because for the last 10 checkpoints, we've needed, 4 WAL segments, we can probably expect that this checkpoint is probably going to need 4 more WAL segments. So based on what we know from before, if we have some sort of redo point here, and this is the sort of end of the checkpoint, then this information from the past, this WAL1 and WAL2, isn't actually useful for us anymore. And we don't need this information because even if the database crashes, we'll be restoring information from here onwards. So what happens to this WAL1 and WAL2? Well, in the smart way that they've set it up, we actually know that WAL1 and WAL2 get their unneeded information removed and they get reused. And this is what would become WAL7 and eventually WAL8, because this information can sort of just become a new segment, and all of this information that's from here doesn't actually need to be stored permanently anymore. So database state can have some sort of new checkpoint here, where information is restored from. And this process will sort of repeat and repeat so we can reuse the same old files. This was just sort of an extra tidbit of information I thought was interesting that I wanted to include. So this has been sort of an overview of how write-ahead logging works specifically in Postgres.